Good. Okay, so welcome to the last lecture of this course. Today, it's a sort of a follow-up on what we have seen last week, which was topology in 1D. I'm focusing on 1D mostly because this is the only thing I barely understand. 2D, but I think the main ideas are there already in one dimension. And actually, historically, the way that people got into were able to understand these topological phases was really starting from one-dimensional chains, actually using this method of which is known as the matrix product state. So it's a way to describe one-dimensional quantum states in terms of matrices that you multiply. The idea of if you have a one-dimensional system, then you can think of it as multiplying, just one matrix onto the other. So that's the matrix product state idea. And those ideas, basically the symmetries of these matrices, this was what allowed people to understand the classification of topological phases in 1D. And then this was further extended in higher dimensions. So I really think, 1D is both simpler to understand and also historically it played an important role. So of course, this is only in every one of these topics, we have seen just the tip of the iceberg of a topic. And if you're interested in more, maybe some of you are working on those topics, so you can explore them in depth. But okay, that was the idea. So last week we had spoken about a topological phase of fermions. Right, this was a very simple topological phase of the SSH topological insulator. And here I'm going to speak about spins. So spins are essentially bosons in the sense that the commutation relations are what matters. But we will see that actually spins and fermions are somehow related. So that's what we are going to see today. So let me start with something that I think most of you have already seen, which is the quantum Ising model. So you all know the Ising model. So the Ising model is just in 1D. So it's just sum over I, sigma zi plus 1, right? That's just the Ising model. You can study it at a finite temperature. Here we are focusing on the 0 temperature case, so T equals to 0. Then if I just have this Hamiltonian, then I immediately know what is the ground state, right? The ground state is just all the spins pointing up or all the spins pointing down. It's very simple. To make the problem interesting, what we are going to do is to add some transverse field. Actually, so basically sum over some x, sigma x I. So so this is a term that actually wants to make all the spins point in the x direction. Maybe you can think of this. Let's actually put it here a minus and here also a minus, so that the ground state is really okay. That's something like this. So that the ground state is really all the spins pointing in the plus x direction. And when you speak in terms of the z direction, then there is a complete uncertainty, right? Because if you point in the x direction, then the z direction is undefined. So you see that somehow these two terms have opposite tendencies. One tries to order in the x direction, in the z direction, and one in the x direction, and make it disorder. So there is a duality transformation between these two terms, so that you can really map one term into the other. We are not going to discuss that. Okay, so what one can do is in order to study the interplay between those two terms, it is common to put a prefactor. So here I put the prefactor on the Ising term. It doesn't really matter. Just this was the reference that I had in mind. But the idea is that there is some ratio. The overall factor doesn't matter. What matters is the ratio between those two terms. And so that's what we have. So what we would see is that if lambda actually, and the key point is there is a quantum phase transition. So we are going to describe that in a moment between a phase that breaks the symmetry and the phase that doesn't. So before we speak about symmetry breaking, maybe let's speak about the symmetries of the problem. Symmetries. And so this problem has, for instance, an Ising symmetry. So what is the Ising symmetry? Ising symmetry. So the Ising symmetry means that sigma zi goes to minus sigma zi. Okay, that's a possible symmetry. Now note that this symmetry actually is anti-unitary. What does it mean? it means that if you just perform this transformation, the commutation relation mess up, right? Because sigma z, sigma x, sigma y is I sigma z. If you never solve sigma z to minus sigma z, then that doesn't work, right? So in order to make it really a symmetry, what you need to do is at the same time to make a complex conjugate of the wave function. So basically, this corresponds. So you need to combine this transformation, so to flip the value of sigma z, and to take the complex conjugate of the wave function in such a way that I will become minus I, and then you are back to the commutation relations. Does it make sense? No. So what I'm trying to say is something simple. I'm trying to say is that the physics is not determined only by the Hamiltonian. It's determined by the Hamiltonian and the commutation relations, right? You need to take the Hamiltonian and the commutation relation. Sigma x, say I, sigma y I, commutation relation equals to I, j, sigma z j, right? That's a commutation relation. And when you perform a symmetry, you need to check that the Hamiltonian stays the same. And you see that, yes, sure, if I take sigma z to minus sigma z, because I have an even number of sigma z, it comes back to its own. So the Hamiltonian comes back to its own, but the commutation relation is broken. So the way to fix it is to say, well, actually, I'm combining this with, say, plus t, so plus a time reversal symmetry, so plus taking the complex conjugate in the wave function, which is equivalent to putting I to minus I. Okay, and once you do that, then everything is fine. So that's why this Ising symmetry is actually what is known as an anti-unitary symmetry. The anti-unitary symmetry means that it combines also the complex conjugation. You also need to take the complex conjugation of the wave function. Okay. So let me give an example. So what I'm trying to say is, think of this state, the state psi, which is, say, 1, 0. When I apply the symmetry, this will become 0, 1, right? I'm taking sigma z to minus sigma z, so I'm flipping the roles. Okay, that's clear. The point is that if I take, say, 1, say, square root of 2i, just to give an example, then this will become square root of 2i minus square root of 2y, 1. So you need to complex conjugate the wave function. That's the way that the symmetry is defined. Okay, so this was a parenthesis. Okay, it's not normalized, but okay. Okay, good. So in a moment this will become important. So that's the symmetry. And now, as I promised, there is a phase transition. So the phase transition occurs at lambda equals to 1. If lambda is larger than 1, then this means that the sigma z term is dominant. So you have in the Ising phase. Okay, so this is the Ising phase. And basically there is a spontaneous symmetry breaking. So it means that basically, what does it mean? Essentially, it means that sigma zi, sigma zj, expectation value, when you take the limit of I minus j equal to infinity, so you take two spins that are far apart, you will see that this commutation relation is finite, is larger than 0. Okay, that's the definition of a symmetry breaking. What does it mean, symmetry breaking? It means that there is a long range order in the correlations. Okay, so this is larger than, okay, it's different than 0. Okay, that's the Ising phase, so it's a symmetry broken phase. In contrast, if lambda is smaller than 1, then the term that is winning is the sigma xi. In this case, the spin pointing in the x direction, there is no symmetry breaking because there was no symmetry to begin with, right? You have applied a magnetic field in the x direction, so you have a given preference. You have given a preferred direction in the, say, the plus x or minus x. There is no symmetry here. So the fact that the spin is pointing in the x direction doesn't mean that it's a spin symmetry breaking, because there was no symmetry to begin with. You have breaking it from the outside. It's not, there is an external field that breaks the magnetic. It's not that when you speak about spontaneous symmetry breaking, something that the system itself is doing to its own. So like in this case, beginning, the system was symmetric. So, but then the system breaks that symmetry. So it displays a long range order in some. So this also means you can also think of this as having an order parameter sigma zi, which is different than 0. But this is the order. This would be the order parameter. But one needs to be very careful with this order parameter. Anyway, so when lambda is smaller than 0, then it's another phase. It's called the paramagnetic phase. And in this case, there is no spontaneous symmetry breaking. Okay, no symmetry breaking, no order parameter. No order. Okay, good. Now, what is the main difference between the ferromagnetic phase and the the ferromagnetic phase or the eigenphase? Oh, it's called also the ferromagnetic FM, ferromagnetic eigenphase, and the paramagnetic phase. So the ferromagnetic phase, in terms of the ground state, there is a key difference. And the difference is that in the ferromagnetic phase, the ground state is doubly degenerate. Why? Basically because you can have either all the spins pointing up or all the spins pointing down. Okay, so when you break the symmetry, when there is the system prefers to say point in one direction because of the symmetry, as we discussed, there is going to be another state, right? So you take the ground state, it points up, but the symmetry tells you, wait, there should be another state, right, with minus the energy because it's time reversal symmetric, where all the spins point down. But clearly, it's so, and it must be another state. So it could be. What the symmetry tells you is that if you apply the transformation to the state, you will obtain another eigenstate. Now there are two options: either the eigenstate is the same eigenstate, or it's another eigenstate. Now, if all the spins point up, when you apply the symmetry, all the spins will point down, so you obtain another state, which means that the ground state is doubly degenerate. In contrast, in the paramagnetic phase, what will happen is that when you apply the symmetry, you obtain again the same state. So it's not, the ground state is not doubly degenerate. Say, if all the spins point in the x direction, when I apply sigma z goes to minus sigma z, I still point in the x direction, nothing happened. And this is true for the entire phase. So that's the key difference between the two phases is the double degeneracy of the ground state. Okay, that's one key difference. Okay, remember this because this is going to be important. Okay, good. So then the question is, how can we solve this Hamiltonian? How can we diagonalize this Hamiltonian? And actually, the way to do that is through something known as the Jordan-Wigner transformation. So remember that everything that we know how to solve we know only to solve the harmonic oscillator. I mean, that's basically the only thing we know to solve, or non-interacting particles. The Ising model is not such a model. I mean, the Ising model is not a model of psi dagger psi. It's not a quadratic model in maybe we know to do Bogoliubov transformations, but it must be a quadratic form. I think there is no quadratic form. So the way to transform into a quadratic form is to use the Jordan-Wigner transformation. I'm going to just give you just to give you a hint of what is done. We're not going to develop the whole transformation. I guess this is going to be a nice homework for you. These are the things I think every physicist doing quantum mechanics must do in one times in his life. Apply the Jordan transformation to the transverse field Ising model. I think it's if you have done it, okay, you don't need to do it again. But if you haven't done it, I think this is a must. Okay, so what is the idea? So the idea is pretty simple. The idea tells you that basically you had what is the idea of transformation? Is taking a spin half and transform it to a fermion. Okay, so in terms of the Hilbert space, the transformation is quite simple in the sense that say you have you have the state up and the state down, and the state up is going to become our one fermion, and the state down is going to be 0 fermion, right? You know that fermions either there is a fermion or there is no fermion. There is no other option. So for instance, that would mean that say sigma zi, which is the number of fermions, the spin, it's going to be simply 1/2 minus 1/2 n. Okay, so psi dagger psi. Right? So if there is no fermion, the spin is plus 1/2, and there is a fermion, the sigma is minus. Okay, that's quite simple, right? Okay, so what is going to be sigma plus I in this? Okay, yeah, in this terminology, what is sigma plus I? Yeah.
creation?
A creation, exactly. So this is going to be, naively you would say, okay, it's a creation operator. The problem is that if you know that spins are not fermions. So, and why they're not fermions? Because fermions anti-commute and spins commute. And if you, for instance, try to, if you try to compute what is the if you use this definition and try to compute the commutation relation of, say, sigma plus I, sigma zi, which you know that it should be sigma plus I, it won't work. Okay, and basically the point is that when two spin operators flip, there is a plus sign, but when two fermions flip, there is a minus sign, right? That's the anti-commutation relation. So how is this fixed? This is fixed by actually defining it a little bit in a different way. In other words, what you do here, you define sigma plus not as the creation operator, but as the creation operator times a phase. And this phase is going to fix the commutation into anti-commutations. And the phase is basically e to the I pi sigma zi. Okay, wait. E to the I pi sum over j smaller than I sigma, well, actually, psi dagger j psi j. Okay, this is going to be our transformation. So, in other words, every time that we create we flip a spin, we acquire a phase, and that phase depends on the occupation of all the sites sitting on the left of our state. Okay, and once you do that, you can check that if you use this definition. Okay, again, this can be done as a homework. If you use this definition, then the commutation relations are fixed. So these additional factors is what allows to transform commutations into anti-commutations. Okay, that's basically the idea. Okay, there is also the inverse transformation. Well, I'm not sure we really need it here. Sorry, this is so sigma plus. Actually, sigma plus should be the creation operator, right? Sigma plus is adding a spin, is splitting a spin up, so it's actually going to be the creation of a fermion. Okay, good. So this is a possible definition, and one can check that indeed it works. The price to pay is that, as you can see, this is a very non-local transformation, right? The spin operators become very non-local. However, there is something very important, which is that when you apply this Jordan-Wigner transformation to the spin model, you actually obtain. Wait a second. Okay. So let me use to make this work nicely. Actually, let me consider the following Ising Hamiltonian. So let's call it H prime. So H prime is the sum over I sigma zi minus lambda sigma xi sigma xi absolute plus 1. So for simplicity, this is a little bit of a diff. Here in the first part, this is the definitions that are common in the spin community, and then you think of the Ising modeling, the Ising coupling in the ZZ direction and the magnetic field in the X direction. But for simplicity, let me actually consider this Hamiltonian, in which let me think of this Hamiltonian in which the magnetic field in the Z direction and the Ising coupling in the X direction. It doesn't really matter. I mean, it's about the same. It's just you flip the roles of the sigma Z and sigma X. Okay, so what is H prime in the fermionic language? So it's minus sum over I. So sigma Zi. Okay, well, sigma Zi it's basically a constant. You see that sigma Zi is a constant, but who cares about the constant? Times psi dagger psi. So basically what you obtain here is just 1/2 psi dagger I psi I. Actually, there's no 1/2 here. This is no. right? There is no 1/2 here, right? It's either 1/2 or 1/2 minus 1, which is minus 1/2, right? This is the correct definition, right? Either 1/2 if there is no fermion. Oh, okay. I see. So yeah. So here in this language, it would be actually the annihilation operator. You know, there are different. I'm trying to highlight the important elements. So implicit ingredients is the following: sigma z simply maps to the density of fermions. It's simple, right? No problem. The problem is this other term. So here you have a plus lambda, and here you need to take sigma x and sigma x plus 1. So sigma x is basically psi I plus psi I dagger. And sigma xi plus 1 is going to be psi I plus 1 plus psi I plus 1 dagger. Okay? However, in addition, you have this string. So let's define this operator here. Let's define this operator here as Si. So this is the string. It's called the string operator. It's the product of the densities of all the sites that come beforehand. So what you need to have here is Si, and here Si plus 1. Okay, this is now exact. Make sense? Not really? Yes? No?
It's okay. You just substitute.
Right, as a substitute. Very good. So now the string has different terms. So in the string, there are some terms that act before I, right? The string is the product of all the sites before the site I. So for all the sites that are before the site I can just simply actually commute. Well, one needs to be careful with the minus signs. We'll fix it in a moment. But basically, you just flip this to the left, and then you have a minus sign. And what happens is that what I'm trying to say is that this is equivalent to minus lambda Si square, psi I plus 1, e to the I pi psi dagger I psi I times psi I plus 1 plus psi I plus 1 dagger. Right? Because what I did, I split this string as all the operators that come before site I and the operator that acts at site I. So all the operators that act at site I don't care. I can, they just anti-commute with these psi operators, and they come to the left. Yes? No?
Why do you have this minus again?
So the minus is because yes, I don't need a minus actually. Thanks. No minus. Okay, so again, let me do it graphically. So graphically, what we are doing is that what I'm trying to say is that sigma. Oh, what's that? What I'm trying to say is the following: that sigma plus I is what? Is the string times the operator at the site I, right? This is sigma plus I. Sigma plus I plus 1 is the same string times the operator at site I plus 1. Okay, so what we can do, we can split it in two parts. There are the parts that come before the site I, and here I get the string times the string. But know that the string times the string is actually 1. So that's important. This is actually 1. This is 1. Why? Because the string, remember, was e to the I pi psi dagger psi dagger. Now, if I take e to the 2I pi psi dagger psi dagger, psi dagger psi dagger is like 0 or 1. So I get either e to the 0 or e to the 2 pi, which is 1, right? So when the string square cancels, and that's great because it means that now I restore the local Hamiltonian. So I don't need to worry about all these fermions that were at sites before I, because I get two strings. Okay, good. And then you are left with this. So what you need to, okay, good. So then you're left with this term. Now here it's actually, the Hilbert space has just two possibilities. Either there is a fermion or there is no fermion. If there is a fermion, then the only terms that contribute, so if there is a fermion, the only terms that contribute is psi I, right? And then this term will give me a minus because there was a fermion. So psi dagger is 1, and then I get the minus sign. In contrast, if there was no fermion, this term would contribute to 1, right? And the only term that contributes is this one, because I can only, if there was no fermion, I can only build the fermion. So what I'm trying to say is that out of the two options, and the Hilbert space is just 2. So either this one acts and then you get a minus sign, or this term acts and then you get a plus sign. So what I'm saying is that this is equivalent to plus lambda psi I dagger minus psi I times psi 1 dagger plus psi I 1 plus 1. Now, if you're not used to work with fermions, you may look at this term and you say, oh, but this looks like anti-Hermitian because it's like something minus the complex conjugate. But actually, everything is fine. Do you want to see how? Or you believe me? Do you want to see what? I mean, this term is an Hamiltonian, so it should be Hermitian. Okay, we agree. Do you want? So, do you see why this term is Hermitian?
Yeah, yes.
You see that. How about the others?
Just this term. This is an equal sign.
Sorry?
Okay, this is
this term, yes, right. So you see, and you see that, let's look at different terms. So I open here a parenthesis. So think of the term psi I dagger, psi I plus 1 dagger. Okay, what is the Hermitian conjugate to it? The Hermitian conjugate to it, okay, let's take the Hermitian conjugate. The Hermitian conjugate is what? Is psi I plus 1, psi I. But this is actually equals to minus psi I plus 1. So now you see that this is why when I combine these two terms, the Hermitian conjugate should be a minus psi I plus 1. So I need, right? That's what allows the system to be Hermitian. So, okay, this was a parenthesis. So this is just a check, a sanity check that indeed the Hamiltonian is Hermitian. But it is going to be also nice for in a moment. Okay, good. So now we have this fermionic system. We can write it in a very compact way. In this form. So you can apply Fourier transform, and then you can write it very compactly as follows, as minus 2 CQ dagger C minus Q. So I mean, you see that it's quadratic form, right? There is a psi dagger psi, and there is also this term which are quadratic, and you see that there are diagonal terms like this one, psi dagger psi and psi dagger psi, and there are off diagonal terms. So my matrix is going to be, oh, sorry, shouldn't be C, it should be psi. Psi Q, psi minus Q, and here I put the psi, what do we put here? Psi Q, psi minus Q dagger, okay, like this. So it's a quadratic form in this way. Actually, we actually sum over all Q that are positive. In a moment, you know, I have a sort of, you know, I need to avoid double counting. So here I have psi Q and I have psi minus Q. So I don't want to count them twice. That's why I'm restricting myself to Q that is only positive. Okay, and this is also the reason why I have this minus 2 that comes out. These are the details. What is important is what lies in the matrix. So what lies in the matrix is 1 plus lambda cosine Q minus I lambda sine Q, I lambda sine Q, and minus 1 minus lambda cosine Q. Sorry, it's a bit, this is sine Q, and this is sine Q. Okay, that's this is the Hamiltonian. And now if this reminds you of what we have seen last week, actually this is not at all by chance. You see, this is also, we can write it as minus Q, something like, you know, think of this as think of this matrix as a spinor. So something like sum over Q, let's call it dq vector, sigma vector, right, as we have done before. And this sigma vector is basically this matrix of, you know, these psi daggers. So the psi daggers are in here, and what I'm trying to say, right, and then we look at this matrix in this way. And what is this matrix? So let's look at the matrix. So this matrix has what? Has a, you see there is a sigma y component to it, right? There is no sigma x component, right? There is no some multiply, there is no real part in here. So there is no sigma x component. And there is a y component, which is a sine q. And there is, sorry, lambda sine q. And there is a sigma z component, right? This is the sigma z component, which is 1 plus lambda cosine q. And then as we discuss, I mean, now what you need to do here is to diagonalize this Hamiltonian, to apply the Bogoliubov transformation. This is a Bogoliubov transformation for bosons, so for fermions. So the Bogoliubov transformation for fermions is just a unitary transformation. As we discussed, when you have bosons, you need to have an you need to use a symplectic matrix, right? You remember there was a symplectic diagonalization, and then we put minuses here and there. That was a little bit more complicated. Here, for fermions, you just need to, you want to rotate this phase, right, in this space. You want to rotate in the space of psi q and psi dagger q. And you know, what you can check, I think actually this was in the homework, to check that if you have a Bogoliubov transformation of fermions, then this is equivalent to just a unitary rotation, just a normal rotation in this space. So what you need to do is to diagonalize this matrix, and what you immediately see is that the energy is just going to be, you know, lambda sine q squared plus 1 plus lambda cosine q squared. So in other words, this is just going to be the size of this vector d of q. Okay. Yes, it's a bit like we have seen, and then you recognize this is exactly the same story that I told you last week, right? That when you draw this vector in the now it's at the yz space. Actually, let's do it exactly like last week. It would be the yz space. You remember that there was either a phase like this or a phase like this, right? When I follow this d vector, the d vector can either cross the origin or not. I mean, either go around the origin or not go around the origin. And this is a winding number, and this will lead to two phases. And there is no way to adiabatically go from one to the other. You need to close the gap in order to have this transition. So it's exactly the same story as the SSH model. What is the difference? The difference is that these are fermions and not spins. Okay. Now, to actually appreciate even more the analogy between these two models, it's nice to introduce some operators that are known as Majorana operators. So note, if you look at this Hamiltonian, so let's look at this Hamiltonian that we had, okay? This is H prime. We can introduce Majorana operators, and Majorana operators are defined as follows. So there is an A operator, which is going to be psi I plus psi I dagger, okay? So it's the real part of you basically split the complex fermion into a real part and imaginary part. So you define two operators, A operator and B operator. The B operator is psi I dagger minus psi I. These are the two Majorana operators. They satisfy some interesting rules, and in particular, so the anti-commute, right, fermions. But the difference is that if you take now AI squared, this is going to be squared to 1. Unlike fermions that they square to 0, right? If you apply psi squared to 0, you get 0. Here they square to 1, or maybe to 2, probably to 2.
They should anti-commute to 2.
Sorry?
They anti-commute to get 2. The anti-commutation relation equals 2.
Right. The anti-commutation relation, right. So the anti-commutation relation is just twice. Oh, so it's 1/2. You're saying? No,
it's 1.
So A squared is 1. Okay. So AI squared is 1. Okay. I mean, but maybe we should. Okay. Let's check it. So what is AI squared? So AI squared is that psi dagger plus psi squared. So it's psi dagger squared, which is 0, plus psi dagger psi, plus psi dagger, right? Plus psi squared. And so this is basically psi dagger psi, right? And this is 1. Right? This is just the anti-commutation of the fermions. So this is 1. Okay, good. Yes, excellent. So these are known as Majorana operators. I'm not sure if they're very useful. I mean, people give to them a lot of it. I think they're just mathematical tool. I mean, it's not anything very very amazing. But what is nice is that you can use this to rewrite the Hamiltonian in a very nice way. So take H prime, there is a local term, this is a psi-Degree psi, and the psi-Degree psi is basically AB. I mean, so the H prime will become sum over I. There is an AI BI term. Okay, there is no A squared term. A squared term is 1. So that's this is, forget about the constants. So the only terms you can get is either AI BI, or, and that is very nice, you actually get another term. So this Ising term, it is basically the B of the site I times the A of site I plus 1. You see? So this is basically plus it would be AI plus 1. So BI AI plus 1, something like this. So this is lambda. This is the Ising term plus Hermitian conjugate. Forgot to mention the key fact. So BI is defined like this. The key fact is that AI Dagger equals to AI. Okay, this is the key property of Majorana fairness. So basically, the Hermitian conjugate of this is going to be again the same term, right? So this term is so when you multiply an A and a B fermion, you obtain something that is Hermitian, right? If I take AB and I take Dagger, what I get is B Dagger, A Dagger, right? Okay. So it's anti-Hermitian, right? So this will lead us to, which is BA, which is minus AB. So we need to put an I actually. It depends. Well, it depends how you define the A and B. If I define it like this way in the I here, then I need to plug in an I here. Okay. Of course, this I is the complex I, right? It's not the index I. So this is J plus 1. Okay, good. So these terms are Hermitian. What I'm trying to say is that you now see the SSH model very nicely, right? There are the two terms. One term that couples two Majorana on the same site, and one term that couples the Majorana on neighboring sites. Okay, so you really have the same picture as the SSH. You either couple the Majorana on the same site, like this. So this is my chain. So there is for each site, for each fermion, there are two Majoranas. There is an A Majorana and a B Majorana, A and B, A and B, A, B, A, B. Now I either couple them together. So I either basically look at the ground state of A and B sitting on the same side. This would be the paramagnetic, the disordered phase, or I couple A and B like this. Okay, and there is a competition between A and B on the same site and A and B on the nearest on neighboring sites. Okay. Okay. Yes.
So may I ask something?
Sorry.
So
yes.
So we were discussing the role of symmetries.
Yes.
In topology. So for SSH, it was important to have chiral symmetry.
Yes.
And here we also have chiral symmetry in this Majorana basis. But like in terms of original spins, which symmetry of Ising model protects?
Very nice, very nice. So that's an excellent question. Let me. I want to. Let me address this question in a moment. There was one comment. I'll answer this question in a moment. I want to make one comment that is related to this figure, and then I'll continue to these ideas of symmetries. Okay. Actually, 10 minutes. I will answer within 10 minutes. Okay, so yeah, it's a good question, but I want to answer that in a moment. So basically, the chiral symmetry, it was the Ising symmetry. Okay, the short answer is that the Ising symmetry of the Ising model is what maps into basically here it would be the time reversal symmetry of fermions. Okay, the fact. So first of all, let me make one comment. So you see that there is a symmetry of the fermions. The symmetry of the fermions is in the fact there is no sigma x component.
No, yeah, like, but for original Ising model, we have sigma z, sigma z.
Yeah. No, the sigmas of the fermions, the sigma of the spins are two different things. They're basically.
I'm just wondering, like, what else can I add to this Ising model, like can I add sigma y, for example, term?
Yes. Well, let me address this question. I'll address this question in a moment. Okay. I mean, first of all, you can do whatever you want. I mean, you can add to Ising model whatever you want. The question is, how does that then translate into the fermionic language? So if I say I want to consider phases that have these, these Majorana phases, right, which have parity. So the two symmetries of the fermionic model are, first of all, it's a quadratic model. So basically, the parity of the number of fermions is conserved. So you either not create a fermion or you create a pair of fermion. Okay, that's property number one. And property number two is that, so this is this just basically charge symmetry, and the other is parity symmetry, and the other symmetry is a time reversal symmetry. A time reversal symmetry means that the Hamiltonian can be written as a real. You see, there are no complex terms in this Hamiltonian, and that's related exactly to the fact that in here you do not have real terms here, which basically means that there is no sigma x. So it's the time reversal symmetry of the fermionic model. Okay. Now you can ask, if I want to preserve those two symmetries, which symmetries do I need to preserve in the Ising model? And actually, the answer is something that we have studied. Not only us, there were two groups working on the same project, but on a similar project. But what we found out is that these two symmetries of the fermions, the C and the T symmetry, the P and T symmetry, map to the two Ising symmetries. So the sigma x going to minus sigma x, and the sigma y goes to minus sigma y. So these are the two symmetries. And then we played a game. I plan to speak about it, but I'm not sure if we have time. We played the game of asking, what are all those phases? So you know that if you take free fermions, basically superconducting wires, so which have a P and T symmetry of fermions, then you obtain an infinite number of phases. And what we asked ourselves was, what are the equivalents of those phases for spins? So if we have time, I'll come back to this point. If not, maybe I can tell you later what was the answer. But let me make one comment which is very important. So you see that like in the case of the Majorana, of the SSH model, what you see is that there are some edge states, right? There is one Majorana that is unpaired. Basically two Majorana, one on the left and one on the right. Okay, so so this would be the paramagnetic phase, the disordered phase, and this is the ferromagnetic phase. It's the parallel of, it's the Jordan-Wigner transform of the ferromagnetic phase. In the Jordan-Wigner transform of the paramagnetic phase, what you see is that there are two Majoranas. Why is this expected? The reason is that these two Majoranas together, Majorana is tricky because they don't have a well-defined Hilbert space. I mean, it's hard to define the Hilbert space. The correct way to proceed is take two Majoranas and build a fermion. And then you know how to build the Hilbert space nicely. Just to build the Hilbert space of Majoranas, that's something I don't think it is. I don't know how to do it, at least. But usually what you do, you think of two Majoranas, you couple Majoranas in pairs, and then this gives you an Hilbert space of size 2. So in this case, what you can do, you can think of, take these two Majoranas, and you build up a fermion. And that fermion, it has an Hilbert space of 2. What does that mean? That means that the ground state is doubly degenerate, right? Why? Because that fermion can either occupy it or not occupy it. Okay, so so in the ferromagnetic phase there are two Majoranas, okay, two Majorana edge states, and these two Majorana edge states are equivalent to the degenerate ground state of the ferromagnet. Right? Remember, I've discussed that the main difference between a paramagnet and a ferromagnet is a ferromagnet has a doubly degenerate ground state. So when you translate it into fermionic language, what you obtain is basically two Majoranas. I mean, these two Majoranas represent the fact that the ground state of the Ising model was doubly degenerate. Okay, that's the idea. Now, you may ask an interesting question, which is, what if what if well, no, I don't want to ask that question. Okay, good, fine. So you see, this is the difference. In the SSH case, what we had were spins half at the edges. So the ground state would be fourfold degenerate because there was a spin half on the left and a spin half on the right. The same in the KLT phase. Here in this case, you have a Majorana on the left and Majorana on the right. Majorana on the right are just a single fermion. So the ground state is doubly degenerate. Now, so this is a sort of well-known facts, but I would like to go into the direction that you were discussing, and which is, how can you extend it to? Can you have more phases like that? And the answer in the case of Majorans is yes. So what you can do is you can consider basically a ladder of Majoranas. So think of a ladder like this. So think of a ladder. Just take two of these chains, okay? Let me see if I can do it. So let's discuss the case of a ladder. I would like to discuss a ladder. So what does it mean? I take this. No, I don't really. Oh, yeah, I copy it. I paste it. This is one. I paste it again, and this is two. Okay, great, nice. So now, this is a system. This is still a one-dimensional system, anyway, very, very, very long. And there are two chains, and this is called the ladder. So the key point of this ladder is that now you have two Majoranas, two Majoranas on the left and two Majoranas on the right. And what one can show is that as long as you consider non-interacting systems, you cannot have an AA term. There is no AA term in the Hamiltonian. As a consequence, these two Majoranas, they cannot interact, and as a consequence, you now have another phase. Okay, it's another phase. It's another topological phase, and you can go more and more, and you can go over and over, and so this will lead to a Z. So. Okay, what I'm trying to say is that if you take, so these are known as superconducting wire. Okay, why superconducting? Because there are those psi terms, right? There is this psi term. It's a wire in the sense that it's one-dimensional. Maybe there are different layers, but overall it's one-dimensional. So superconducting wire with PT symmetry. Symmetry. So there is a parity symmetry, meaning that fermions are only born in pairs, and there is a time reversal symmetry, meaning that okay, as we mentioned, the Hamiltonian is real. I mean, there are no terms. There is no I in the Hamiltonian. Okay, that was the idea. So people have studied the classification of those phases. Okay, there is a well-known classification of all the topological phases of topological non-interacting fermions. What you will see is that if you go in one dimension, you have this PT symmetry. You will see that there is a Z classification, meaning that you can have as many, that you can have many different phases, and these different phases simply correspond to putting many chains like that, one after the other. Right? Good. By the way, there is both positive and negative. The negative would be if you put the B on the left. Okay, if you have A on the left, and the more A's you have, the more the upper you go. Right? The more A's you have, the more you have edged Majorana fermions on the left. If you instead put a B, if you take a chain like this with the opposite direction, then you see that you obtain a B and an A. The A and the B, you can couple them together and get them out. So this could be like a get fermion. It's not anymore a protected edge state. So the more A's you put, the more you go on higher. This winding number grows. Remember that this is all overall. This is what I'm trying to say. Something very simple, which is just that you can. This is equivalent to asking the question of how many winding numbers I have. How many times do I go around the zero? Okay, so when you have the one Majorana chain, it's going around one time, and if you go and if you have two Majorana chains, it's like going twice, etc. And then you can go clockwise or anti-clockwise. Okay, these are all equivalent description of the same problem. Okay. So what I would like, so this is just to say that there is a generalization. So it's not, you can think of the wire, then you can go to the ladder, and then you can go to a ladder with more and more layers, and you get more and more topological phases. At least this is in the no-interacting case. The interacting case is more complicated. It turns out that you can have up to 8 phases. After that, you go back to so it turns out that if you have 8 A's on the left, you can couple them together. If you have an interacting theory, you can couple all the 8 A's together and then gap out the edge state. So that's why you can have only up to 8 Majoranas, not more than that. If you have an interacting theory, so this is Kitaev and Fitkowski work. But let's put that aside. So thinking about non-interacting fermions, you can have as many layers as you wish. What I would like to ask today, in relation to the experiment that I'm going to show you, the experiment that I'm going to show you on something we did, it's related to the question of reverse engineering. So I told you that there are more and more topological phases of fermions. And the question is, how do these phases correspond? It's a little bit going in the direction that Paulina was suggesting. How do these phases look like in the spin language? So what we have seen is that the phase, so let's call W. W is going to be this winding number, okay? So W equals to 0. Okay, W equals to 0, no winding number is the paramagnetic phase, okay? It's there is no, it's the topologically trivial phase, there is no winding, and this is going to be, it's the Hamiltonian in the spin language is just a sigma xi. Winding number 1, okay? You get sigma zi plus 1, right? It's the ferromagnetic. As we discussed, the ferromagnet, I told you, the ferromagnet is the phase in which you have one Majorana at the edges, and it's equivalent to going 1 times around it, okay? How about having more letters? So what we have found is that, so you need to be careful. Let me tell you what is the trick. The trick is that you want to apply Jordan-Wigner transformation. The Jordan-Wigner transformation is a one-dimensional transformation. So, but this is a ladder. So you need to define how do you apply the Jordan-Wigner transformation on a ladder. And the way we did it was something like this. So we go up and down like this. You see? Okay, we go zigzag. So by going zigzag, what happens is that actually, you see, the coupling between, so this is basically, let me put numbers. So this is going to be, let's use a different marker. Okay, so this is going to be 1, no. This is going to be 1, 2, 3, 4, 5, 6. Okay, this is the way that I order my fermions so that I can do Jordan-Wigner. Okay, each of these bubbles is a fermion, and I need to do Jordan-Wigner. So what you see now is that the Hamiltonian actually has a coupling between the spin number 2 and the spin number 4. Right? Each of these fermions is mapped to a spin, but the ladder has an interaction between 2 and 4. So it's not anymore the interaction between nearest neighbors. There will be a spin interaction between next nearest neighbor, okay, which is equivalent to having an interaction between fermion 2 and fermion 4. Makes sense? Paulina is not convinced.
So I'm just thinking, like, why do you need this zigzag?
Okay, because I want to apply Jordan-Wigner. So in order to apply Jordan-Wigner, I need all my fermions to be in a line.
But why you cannot have like 2 Jordan-Wigners for each?
No, because you see, then this would not satisfy the anti-commutation relation. It would work nicely for the anti-commutations between fermions on the same line. But I need also to make sure that fermions on the two layers also anti-commute. If I have only a string on the upper one and the string on the lower one,
then they will commute.
Then the two, if they belong to a different layer, they will commute, and that's bad because they are not fermions. So the way to solve it is to actually have one string that goes over all the system, and then in this way I make sure that all the operators anti-commute. Okay, so what you see is that if you, I mean, that's what we did. I mean, maybe there are other solutions, but what we did was this one. And then what you see is that you obtain now a coupling between, direct coupling between two fermions that are one side apart. If the two fermions are one side apart, then the string between them is going to be significant. Okay, and indeed, if you do this carefully, what you will see, and this was a work of Batel Friedman, who graduated a few years ago. What we did, and there were also related works in other. What we saw was that what you obtain is a sigma zi, sigma x I plus 1, and sigma z I plus 2. So this string that was in between. So first of all, you see that there are interactions between nearest neighbors, but the strings basically plug in some additional term in between. Okay. So and this Hamiltonian is actually a topological Hamiltonian. Okay, so note that this was just a disordered Hamiltonian. In the fermionic language, W equals to 1 is the Majorana, the famous Majorana chain. I mean, if you've heard, by the way, about Majorana topological quantum computing, these are the same Majoranas. So it's something very topological. In the spin language, it's very simple. In the spin language, it's just an ordered phase. It breaks the symmetry. For winding number 2, what you obtain is actually a phase that it's really a topological phase for spins, okay, which will have also edge states. That's related to the fact that in the spin language, what you need to have are spin edge states that require two Majoranas or a fermion. So you need an even. What we found is that every time you have an even number of winding numbers, this maps into a topological phase. Every time that you have an odd numbers, this maps to a phase that breaks symmetry. Okay, so that was the work. Okay, so I think we should stop here. What I just want to tell you in one sentence is that I told you about these 8 phases that exist for interacting fermions. In the case of interacting fermions, there are 8 phases. This is the Kwiatkowski and Kitaev work, where I told you that 8 A's can be combined together into 0. It can be gapped out. So you basically have winding number 1, 2, 3, 4. And when you have 8 winding numbers, you can actually dewind. You can use the interactions to dewind them. Okay, that's sort of that's the idea. What we have discussed, what happens in the spin model. In this spin model, you have a richer situation because you can either have phases that break a symmetry or phases that do not break a symmetry. And if you have 2 Ising symmetries, so I mean, but eventually everything works. So these 8 phases correspond to either topological or ordered phases of spins. And we have really seen the classification. So you can really use Jordan-Wigner to study interacting phases of fermions. You can use the classification of spin models to derive a classification of interacting fermionic models using the Jordan-Wigner. Yes.
Why 8? Why not?
It's a weird number.
I mean,
Why
it's
8?
a good number. It's the best number.
It's a good number.
So first of all, you need, okay, first of all, odd numbers. Okay, first of all, there are no odd numbers in the Hamiltonian. Because you only have, I mean, you need to preserve the PT symmetry. So you can have Psi-Dagger Psi or say Psi-Dagger Psi square, but not Psi-Dagger alone. That is not allowed. So there are no odd terms. Now, so naively, okay, so what is an interaction term? An interaction term, it would be something like Psi-Dagger Psi, Psi-Dagger Psi, right? That's the interaction term that you are trying to use. So you see that naively, this would include 4, it's a 4 Majorana term. So naively, you would say, maybe this term, maybe it could be something like A1, A2, A3, A4. If you have such a term, then this term will mean that you gap out the excitations. However, it comes out that this is true, but it doesn't gap out all the edge states. Because to begin with, you had, you have now 4 edge states, 4 Majoranas, and what this does is to gap out some of them and not all of them. I don't have a very good, a simple explanation for that. In contrast, if you allow, products of the 8 Majoranas, then you have a richer situation, and you can gap out all the Majoranas. So in the sense, it is, I mean, the phase for Majoranas indeed has a lower, it doesn't have all the ground state degeneracy. The ground state degeneracy is a bit lower. So some of the Majoranas are gapped out, but not all of them. Okay, that's what comes out. So it's not really, it's still topological. In the case of the spins, this is related to the number of phases or topological phases that you can have in interacting models of spin. I mean, spins are always interacting. So, but I mean, you can read the paper if you're interested in more details. Okay, that's what I wanted to show you. But I'll show you. Okay. Okay. Let me move to. Okay. Let's take a 2 minutes break. I switch to the other computer, and then I show you something about the experiment. Okay, so 5 minutes. רגע, אז אתם לא רואים. רגע, אז מה אני עושה פה? איך הייתי עושה את זה פעם?
נראה לי פשוט היית מעביר להוא, לא?
רגע, אני פותח... רגע, ואם אני עושה... כן, בדיוק. אם אני עושה כאילו זה, לוגין מפה, ואז אני נכנס כאילו. אני עושה share מסכנים מפה. אוקיי, let's see. אוקיי, בסדר. with computer only.
כן, ואז נשמע.
אוקיי.
מה לא נדבר?
שאל את החבר
Do
בבית.
the people at home hear us? Anyone awake?
Shai, Quancheng, Isaac, someone is listening?
Hey.
Yes, we'll see.
Yeah, I can hear you.
Okay, excellent. Okay, great. Okay, so this was, this is the table taken from this paper. So I told you that there is an Ising symmetry in the z direction and an Ising symmetry in the y direction, and then you can either have, and these are time reverse anti-unitary symmetries. So you can either have both of them, and if you have both of them, it turns out that there are 4 different phases, 4 different topological phases. So this gives you 4, or you can break one of the symmetries, and then you can have so if I break the y symmetry, I still have the z symmetry, and this leads to 2 topological phases that break one symmetry but preserves the other. So eventually, what we showed in this paper is that you can build these 8 phases out of using the spin terminology. Okay, what is shown here is that this is the symmetries of the problem, and these are the cohomology group. So the cohomology group tells you what are the properties of the topological phases. So this is the symmetry of the problem, and this is how many topological phases you have. So if you have, say, 2 Ising symmetries, then you can have Z2 cross Z2's overall 4 topological phases. Okay, or you can have only one of them. So, but okay, again, the details are in that paper. It's just to say that we know what the answer is. Okay. So how about the experiment? Okay, this is lecture 12. Okay, good. So, okay, that's something that basically we discussed, that in terms of the spins, there are, one can think of a model that has 3 different phases, an ordered phase, a disordered phase, and so now what we did in this experiment was to realize experimentally these phases using quantum computers on the cloud. And what you need to understand is that when you use a quantum computer on the cloud, you're actually preparing a quantum state. So unlike a condensed matter field systems that you have a system, a Hamiltonian, there is a Hamiltonian, the dynamics is determined by the Hamiltonian. Here the dynamics is determined by the gates. So it's not really an Hamiltonian, but what you can do, you can think of preparing the ground state of that Hamiltonian. So in this case, preparing the ground state of the sigma z Hamiltonian is very simple. Just do nothing. All the spins point in the noun direction. That's the ground state. In the case of the sigma x Hamiltonian, this would the ground state is just preparing all the spins in the plus direction, and this can be obtained by applying an Hadamard gate. So you know that the Hadamard gate is preparing the superposition of 0 and 1, so it's just the plus x direction. What turns out is that it's actually also simple to prepare the ground state of this Hamiltonian. So this specific Hamiltonian has a ground state that is known as the cluster state, and is prepared by preparing the superposition of all the possible states, and then applying these are controlled Z gates. So these are gates that give you a phase if all the spins point in there. So this is like e to the I pi sigma zi plus 1. So only when the both spins are up, then you acquire a phase of minus. Okay, so you obtain, a huge superposition of all the states with a phase that can change depending on the occupation of neighboring sites. And this state is exactly, and again, actually, one can almost read it out from this paper, that the ground state of the output of this state is the ground state of this Hamilton. Okay, so I would like to discuss today two experiments. One was performed in a group of Titus Neupert at ETH. So what they did was the following. First of all, they prepared such a state with 8, actually it's a cluster state with 8 spins, 8 qubits. And then they looked at the reduced density matrix. So how does the reduced density matrix look like? Let me first discuss the case of the trivial paramagnet. In the trivial paramagnet, I should have, this should have appeared one by one. So, but let's try to focus on the left, on the trivial paramagnet. So in the trivial paramagnet, the states just all point in the 0 direction. So, right, this is a pure state. It's just very simple state. So what is the reduced density matrix? Well, the reduced density matrix, the eigenstates of the reduced density matrix are just, first of all, the reduced density matrix is a 16 times 16 matrix, right? Because if you integrate out 4 spins, right? Then the maximal size is going to be 2 to the 4, which is 16, right? If you want to describe a system of 4 spins, let's say I focus on the remaining 4 spins, then the eigenstates, then the basis of the remaining spins is 16, right? You have 16 states. So the density matrix is a 16 times 16. The density matrix of 4 qubits is a 16 times 16 matrix. It has 16 eigenvalues. Now, in the case of a very trivial state, just all the states pointing in the 0 direction, when you integrate out some part of the system, who cares? You obtain also a reduced density matrix which has just 1 and then all zeros. Right? The system is just in 0, 0, 0 state. Yes? Yes, good. So this is how it should look like. In reality, when you do it on a quantum compute. So this is the ideal, means this is a noisy simulation, and you see that, well, the 1 is not really 1, but still it's almost 1, and this is it done. This is the experiment, and what you see is that, well, basically you obtain a lot of values here and a few values there. Let's now move to the second state. So this is the cat state. This is GHZ state. So it's 0, 0, 0 plus 1, 1, 1. The superposition of all the qubits in 0 plus all the qubits in 1. In that case, when you integrate out part of the system, what you obtain is density matrix that has 2 values that are equal. One for the z. It's like being basically in a mixture of either 0, 0, 0 or 1, 1, 1. Right? That's what happens when you integrate out the GHZ state. So the density, the eigenvalues are either 1/2, 1/2. I mean, all are 0 except 2 eigenvalues that are 1/2, 1/2. 1 for the 0, 0, 0 and 1 for the 1, 1. Okay, good. Now, how about this SPT phase? This is the cluster state. Okay, so the cluster. So here one needs to introduce something known as the edge-bulk duality, which is telling you that there is a relation between the edge state of a subsystem, sorry, the edge state of open boundary conditions, and the reduced density matrix of a periodic boundary conditions. Actually, this experiment was performed with periodic boundary conditions. Okay, so actually the first qubit was connected to the last qubit. Okay, so there are no edge states. The ground state is singly degenerate. There is no edge states. It's only when you open the edges that there is this degeneracy, this wingling spin house. If you close it, then no edge state. So the ground state is uniquely defined. However, when you integrate out part of the system, it is a little bit as if I was creating an edge state. Okay, that's not something that I will later on. I will try to give you a better intuition for that. But for the moment, accept my intuition that by looking at the reduced density matrix of a subsystem is a little bit like opening an edge state. Is a little bit like creating an edge. Okay, this was the idea that was put forward by Duncan and Dane, and also extended to 2-dimension. So it's a very, in particular, in this case, as I mentioned, because there are these two wingling spin half at the edges, okay, this is a 2 winding, or the winding number, if you want, is 2. So there are 2 Majoranas at each side. So that these 2 Majoranas is like a spin half on the left and a spin half on the right. Okay, so there are 2 edge states. And as a consequence, when you integrate, so there are the degeneracy, if you had open boundary conditions, the degeneracy of the ground state would be 4. Here, something similar happens in the sense that when you look at the reduced symmetrics, you obtain a degeneracy of 4. Okay, so again, you see here that the ground state, that the reduced symmetrics has 4 degenerate edge states, and then all the other edge states. Okay, and this was probed in the experiment. So here you see one realization of the experiment. You see that there are 4 edges that are far above and many edges that are below. Then if they repeat the experiment many, many times, then, well, the idea is that still you can sort of identify 4 that are above some gap. And so they're not really, they should be degenerate. I mean, if this was a topological phase, I'm going to explain that better in a moment, but the key feature of the topological phase is that these 4 edges are degenerate. Okay. So we have basically extended this idea, and by looking at something known as the symmetry resolved topology, so that is known as the symmetry resolved reduced symmetry. So what is the idea? The idea is following. What does it mean to have a symmetry? Having a symmetry means that there is an operator who's such that the ground state is an eigenstate of the operator. Right? Let us see. What is an symmetry? Is an operator that commutes with the Hamiltonian. If there is an operator that commutes with the Hamiltonian, you can always find the ground state, so the eigenstate of the Hamiltonian, the ground state, in a way that it is also an eigenstate of the symmetry operators. Right? You can diagonalize together the Hamiltonian and the symmetry. Simple, right? Now, what happens for the reduced density matrix? Turns out the reduced density matrix is not anymore an eigenstate of the symmetry. However, in the reduced density matrix commutes with the symmetry operator. Let me explain you this with an example. Think of a system in which there is a conserved quantity number of particles. I take a box, I put in 50 particles. Okay, so the eigenstate, the ground state, has 50 particles, so it's an eigenstate of the number of particles. If I do now, and these particles are in superposition of the states, right? They are not localized. Now I integrate part of the system and look at subsystem. In the subsystem, well, the number of particles fluctuates, right? Because I can have any number between 0 and 50. However, what comes out is that the reduced density matrix is still block diagonal in the symmetry operator, meaning that I can diagonalize the reduced density matrix within the number of particles. So the total number of particles is not conserved, but is well defined. I mean, I have a statistical mixture of different number of particles. I will not have a superposition of different number of particles. Let's say I will have either 25 or 26 or 27. I will not have a superposition of 25 and 26. That's related to the way that you integrate out. How you integrate out? When you integrate out, you put you put in the brine the cat the same state. Well, this is something you need to think about it on your own. It's a very simple theorem, but one need to think about it. So what does it mean to integrate out? To integrate out means that you assume that the brine cat state of the part that you are not looking at is the same. Right? You trace over. It's a partial trace. Right? That's it, to integrate a partial trace. So it means that the brine and the cat are the same. So you don't know how many particles you have in. Let's look at the system that you are not looking at. In the system you're not looking at, you don't know how many particles you have, but you know that it's not in a superposition of different number of particles. It has a well-defined number of particles. I don't know what it is, but it is well-defined. So what this means is that the reduced density symmetrics will always block diagonal in the symmetry. Okay. Now, in this case, we have a Z2 symmetry. So there are only 2 blocks. Okay. Actually, it should be 4 blocks. For reasons that I don't want to dwell into. Actually, we had only 2 blocks. But so that's just the definition of symmetry. Symmetry means to have blocks. That's the symmetry. Just a definition. This is not topology. Symmetry. Symmetry means to have blocks. Okay, haven't used topology. However, what is topology? Topology means that the blocks are equal. So what is the topological phase? The topological phase is a phase in which the blocks that exist because of the symmetry are equal. So it's a particular type of a symmetry. Okay, that's what so what is the difference between topological and the topological trivial phase? In the topological phase, you can have the reduced symmetrics, the blocks are different. In the SPT phase, the two blocks are equal. So this is really related to this degeneracy that we have seen here. You see that the fact that all the you have seen that I told you that here there are 4 eigenstates of reduced symmetries are all equal. That's really the key feature of the topological phase. And so that's what we did. So what we did, we took a system of 4 qubits, and then we looked at the 2 blocks, actually trace of the 2 blocks. So the red and blue are the 2 blocks. LA is the size of the subsystem. So if I take LA equals to 4, that means that I look at the whole system. Now the whole system is in a well-defined sector. However, when I look at because there is no, okay. When I look at the subsystem has these 2 sectors. The subsystem has two sectors, and the 2 blocks, which is 2 blocks that are equal. So that's why in the subsystem, the 2 eigenvalues, the density matrix has 2 eigenvalues that are equal. Actually, the trace of the 2 blocks is the same. That's at least in the simulation, even in the noise simulation. In the experiment, as you can see, the 2, I mean, the overlap is not perfect. Okay, and the reason that the overlap is not perfect is actually also something that we understood. It's related to the fact that in the measurement process, there is a difference between 0 and 1. When you measure the qubit, there is a difference. Naively think of a single photon detector. When you have a single photon detector, you don't see a photon. There could be 2 reasons. Either there was no photon, or you haven't seen it. So if you see a photon, then the photon was there. So if you see a photon, you're in the 1 state for sure. If you see 0, I don't know. Meaning that there is a preference towards 0. Okay, when you measure the qubits, and that's true also in the superconducting circuit, when you measure the qubit, there is a preference of measuring 0 with respect to 1. And so this translates into breaking the symmetries. As if I didn't have the symmetry that protects the topology. In order to have the topology, I need to have these blocks, right? And the blocks are there because of symmetry. If there was no symmetry, there was no topology. So this is why these are called symmetry protected, not symmetry resolved. Symmetry protected topological phases. You need to have protected. Symmetry protected topological phases. You need to have the symmetry in order to have the topology. So you see, as you see in the experiment, the symmetry is broken. It's broken just a little bit. So, this blue and red, this is a non-topological. In the non-topological, blue and red are far away. So the blue and red are, well, not too far apart, but still they are far apart. So and there is, we are not really, there is not really, the symmetry is not perfectly conserved. Okay, yeah, that's what I wanted to show you. We also related that to measurement-based quantum computer. We definitely don't have the time to discuss that. Just wanted to point out one paper that appeared very recently that is somehow related. Actually, I noticed that only yesterday, so I didn't have time, by the Google group. This is basically the latest paper by the Google group. Let me just show you the title. The paper. Yeah, I'll open it up. Accurately computing the electronic properties of a quantum ring. Okay, so this is a paper on the Google quantum computer, and they realize they realize basically one-dimensional wire of fermions using qubits. So this is related to this Jordan-Wigner transformation in which you map spins or qubits into fermions. Then they can even apply something that looks like a magnetic field, and so on and so forth. So you see, this is this is the band structure. I mean, this is the band structure of the band structure. This is the band structure of the spin model, which is the same as the fermions, right? So they use this mapping to study fermions using spins. Okay. Okay. Really, I didn't have time to look into the details, but you can. Okay. that's it. So thanks for listening. And again, I called the homework we submit. Yeah, so Quancheng, are you ready for your presentation?
Yes, yeah. I share my screen. Yes, yes. So can you see my screen now?
Yes.
Okay, so hello everyone. Today I will present to you some experimental realization about the quantum walk. I will first introduce some basic concept of the quantum walk, and then I will focus on the case that was realized the quantum walk by the quantum computer. So let's start. Okay. So the quantum walk is the classical. So that long time ago, when there was the classical random walk, and then the quantum walk is its quantum analog. So let's say there are difference. So first of all, this is the classical random walk that we have the for example, the worker is the red ball, and it's, for example, it can initially go stay at here, and then it jump to its surroundings according for example, according to the spin, the spin, for example, you toss a spin, and then if it's side one, then you go to this term, and if it's side two, then you go to this term. So this is the classical case, and this is what we will say that if you do the experiment. So this is we will say that the probability distribution of the worker is that it's like a Gaussian distribution and mostly focus on its starting point. So, but for the quantum case, the story is a little bit different because of the superposition of the quantum state. So first of all, that now you also have a quantum worker, but now it can go to these two sides, but because of the superposition, and then after you involve some time, you will say that the probability distribution of the worker is very different from the classical case. And we say the tendency of the quantum worker is that it will spread to its edges. So this phenomena is as a comparison of the quantum case and the classical case, and we will say the quantum case have a better ability in transporting the system. For example, if this is our message and you have a receiver at this at here, and compared to the classical case, a quantum random walker will send the message more efficiently. So, but there are two ways to define the quantum walk. One is the discrete time quantum walk, another is a continuous time quantum walk. So the discrete time quantum walk is very like the classical case. So first of all, you have a coin flipper that is like a classical coin. You toss the coin, and then conditioned on the outcome of the coin, you will shift the for example, the particle. So the total state of the system can be written as two parts. The first part is for example, its position parts, and the second is like a spin. So usually people do that they use this Hadamard metric to rotate the spin, so the probability of jumping to the right and to the left is equal. So, and you have the condition shifter, that is, if the outcome of the spin is up, then you move from the I to the I plus 1. If the outcome is down, then you move from the I to the minus 1. So you move to the left side. So the full picture of the discrete time quantum walk is that first of all, you have the Hadamard matrix and that rotate the spin, and then condition on the spin, you shift the particle. So this is the discrete time quantum walk. And then there is the continuous time quantum walk. That is, now the system is involved according to the Schrödinger equation. For example, if we consider this case as a tight binding model, and then its Hamiltonian can be simply write like this. And then what you do is that you involve the system according to this Hamiltonian by the Schrödinger equation, and you will say is distribution, the probability distribution of the quantum work. So this is a very brief introduction to the quantum work, and I will focus on the introduction, not on the experiment part. So there are many different realizations of the quantum work, because, for example, we say that we are considering a tight binding work, but in the UX, sorry.
No, there's just some noise in the corridor.
Okay, so, but you cannot say, for example, you inject an electron to a solid and then make it work. So the quantum work experiment are realized by, like just we heard in the course, that we mapping the system, this quantum work system to other system that to realize the quantum work. So for example, there is so this is for example, there is an experiment realized by the optical trapped ions. That is, you have the laser that to produce a field, and you inject you inject atom, and this atom is like our quantum worker, and you make the atom work in this optical field. And also there is trapped ions a lot of ways. Also, this one is realized by the waveguides. That is, you inject a photon to a waveguide, and these waveguides are coupled to each other like a tight binding model. Then the photon will jump to the right or to the left, and then you will have the image that is in the end to see the work picture. And also this picture is for this one is use the trapped atoms. But this is the discrete quantum work case. So you first prepare the system, and then you toast the core and you shift it. So these are like previous experiment, but now with the development of the quantum computer, more people are start to focus to do the quantum work by the quantum computer. So this is the main topic of the presentation. So that was the quantum work with the quantum computer. I will mostly focus on these two papers. So this one is published 2 years ago, and this one is on this year. And the 2 years ago is use 12 qubits, but 2 years later they make it 2-dimensional and also more qubits. So what is the idea? The idea is that because this is a qubit system, and each one is a small qubit, and is coupled to its surroundings, and also this small thing is the control line. So this system can be effectively described by the Boson-Hubbard model. So this is this Hamiltonian is the. So this describes the qubits, and this some energy, and this is the coupling between its surroundings here, because this is a very specific system, because it defines several groups. So this 4 is a group, because this one can only connect to these 2, not to this one. So this is the Hamiltonian that describes the system. And what they do is that they tune the system such that the frequency of the qubit of each qubit are equal. So we can effectively neglect this part, and also this part they consider some limit also neglected. So what we are left is that we only the effective involution Hamiltonian is just by this Hamiltonian. So we can say this is simply if we connect to what I just discussed previous, is that this can be regarded as a tied binding Hamiltonian. So we can use this. So we can use this system to perform a quantum work, the quantum work, just like what we study or even study in the theory. So this is what they do. So this is their qubit system, and so here they have the 12 qubit, and why is not used, because why is used? I read the paper, but I do not say, but but why not use? They only do 11 quantum work. Yes. So and this is their control line. This is the z direction control, and this is the XY control. So first of all, that is what they do is that they first. So the first step is you need to prepare a quantum work in the system, and what they do is that they buy. So initially they make all the qubits are in its ground state. So it's like there's no work in the system. And what they do is that they first apply a X gate to the 6 qubits. The number is 6. So it's like in the middle you create you transfer the 0 state to the 1 state. So this state will represent the quantum work, and it's like we initially inject a quantum worker into the system, and this is our worker. And then in this time period, they turn all the qubits on, and it will evolve according to the Hamiltonian that I just showed. So the quantum worker will jump to its nearest, and it's spread. So this is a theoretical result. This is the velocity of the diffusion. And this is for the single quantum work case, and also this two picture that they also study 2 quantum work case that is by excite two qubits. So 1 qubit represent one quantum worker, and 2 is 2. And also they also study a little bit about the correlation between the state, but I will not discuss this in detail. So this is the full diagram of this qubit line. And this is the readout line that is connected to the z direction. And also this one is used to control in the XY direction. So let's see their results. So first of all, as I just said, that they initially prepared the system at the qubit 6. So this is their initial state, and this is their experimental result, and this is their theoretical simulation. So the quantum worker will diffusion or jump to its surrounding, and then with time evolving, they will spread to the system. And the experiment and the theoretical compare agrees very nice, I think. And also they studied the case that they start from the left side and also from the right side of the qubits. That was initially rather than excite the qubit number 6, we excited the qubit number 1. And then this is how the worker works in the system. And also this is the theoretical prediction. We can see these two pictures also agrees quite well. And also this picture is for the 2 worker case. That is initially they excited the number 6 and also number 7. And also these 2 worker goes to the spread to its surroundings, and then they have the plot. And also this is the one from 1 and another from 0. So here they use 11 qubits, but here they use 12. Okay, sometimes they change it. Yes. So and this one is for the so the previous is that it's a 1-dimensional quantum work, because their qubits are aligned in a line. Are put in a line. So now this is the case for the 2-dimensional quantum work. That is, they use this processor. So and this is their result. So initially initially they prepare this is their initial state of the system. They prepare 2 work in the system, and this is their initial state. And also this is they do the simulation to compare, and then they turn on the time and then make the system to work, and then this is their results. And compared to the theory, this time is also, I would say, it's also very nice, because this is already a very large quantum system. It has 62 qubits. So, and they control their noise to a very low level, and their result is quite good. Yeah. And also they do more than that now, because so previous is like we just do a quantum work and to turn on the system and do the measurement and then do the statistics and plot the diagram. But now they introduce the control into the quantum work. The concept is that by by tuning the qubits, so by tuning the frequency of the qubits, they let the quantum worker can only go on these two paths. So this is the whole qubits, but now, so they tune these qubits into the frequency, if I remember correctly, so it's 5 gigahertz. And these qubits are into 4.9 or 0.8, something like that. It's different frequencies, and then this produce that the quantum worker now can go only on these qubits, but not these. So now this is their starting qubit. They start from here, and this is their starting everything. And they first let the qubit to go to this. They first let the quantum worker to go to this qubit, and when they reach this qubit, they have two paths now. So the left path and the right path. So the quantum worker will go on this path or on this path, and this is their result. So as we can see that this is the path. This is path left, and this is the path right, and finally it goes back to this and transmits to this. So this is the final result. So it's like the quantum worker first separate at this place, and then they come back and to this final state. And this setting is just exactly like interferometer. So they also by controlling the coupling strength, they are kind of changing the path, the length of the path that the quantum worker goes. So they can have an interference pattern. For example, you make this route a little bit longer, or you make this route a little bit longer. So there will have a phase difference, and you will have a constructive interference or destructive interference at this place or this place. And this is what they see in the experiment. And again, this agrees very nicely with the numerical simulation. And also to say this is the real interference, they cut the path. So they also tune this 2 qubit to the frequency of 8.9. And then now we can no more see the interference. It's just it's just this. Okay, so they also consider the case for the 2 quantum workers. So now they have 2 quantum workers in the system and to observe this interference phenomena. So initially this is also their path, but now this is they first prepare the quantum worker here and also another one here, and they let the system evolve, and they see again the interference, but very similar to the one quantum worker case, but this time it's 2 quantum worker. And what is very interesting is that when they disconnect these 2 qubits, it's like they turn off these 2 qubits and prepare 2 qubits here. So what the difference between these two settings is that at this place you can go back. So you can from R1 to BS1. But here you can no more go back. You can only propagate in this direction. So in this sense, these 2 quantum workers now cannot commute. So they cannot propagate into this. The L1 cannot go to R, and the R1 cannot go to L. But now they can no more see the interference. I think this is a very interesting result. Yes, I try to find explanation in the paper of why, but not. But this is very interesting. And also they also do the one worker case because of the inspiration of this by this setting. This one they excited the system here and no more here. Again, they see the interference. And also for the R, they see the interference. But as a reminder that these 2 interference patterns is different, because we see the path to go from here to here is not equivalent for the here to here. So this is their nice result. So, but do we have a chance? I want to thank the Emilia to give this nice idea, that is to also we see this quantum computer in the course again and again. So, and now we are trying to work on to because they have their own, they are the people works in the experiment, and they have their own device and they can do this. But now it's available on the cloud or the IBM quantum computer, and we want to do very similar result. And I hopefully the answer is not very likely, but yes. So maybe we can also do a quantum work, but with more physics and with more something more interesting. So thanks to Emanuela for this nice course, and also I want to thank Emanuela and more for the great help in the research. So that's all.
Okay, thanks a lot, Quancheng. This was a very nice presentation. Yeah, so actually, More and I have some thoughts about it. Turns out it's not that simple. And in particular, what was unique about the qubits used in that system is that they can tune sigma, the splitting. So they can basically plug the energy of each qubit to 0. And that's something that one cannot do it, at least not in a trivial way in these computers. So they have basically, those computers have an additional knob that allows them to really shift the energy. And here this is not present. But okay, it doesn't mean that it's not impossible. It just means that it is a little bit harder than we thought at the beginning. Okay, well, then thank you again. I hope that you enjoyed the course and then that you learned something new, and that you will, maybe this will help you with your research, trying to apply this for experimentalists to try and relate what you are doing to, bigger as idea coming from theory, and from theoreticians trying to, having a broader perspective of experiment that could be relevant to the equations that you are studying. Okay, so then thank you.